Swayam Prabha. Digital India. Educated India.
Okay, so we are looking at directional stability of airplane, and we are talking about the motion of airplane in XY plane, right. Right. So, that is the rotation about the z axis that we are talking about, and if you remember I said, let us say there is a level flying condition that the airplane is flying, right, going straight along this line, and suddenly, so this the velocity is also along this line, okay, only straight line path is going on with this velocity, let us say v, right. Suddenly it sees a gust which is from this side, and that will result in a side slip angle. So, now new velocity vector would be something like this, right, and the angle between these two is called the side slip angle in this plane XY plane, right. So, this beta is a small beta introduced by a gust of wind, okay. The wind is not a constant wind, it is not staying, right, it is coming and hitting the airplane and going back, right, and that is how we talk about stability. We want to look at the stability of a system with respect to motion that it shows when you disturb it, right. So, if you look at this picture, the aircraft should be able to kill this beta, right. So, that is what is meant by the stability, is not it. So, look at the this pendulum model, and let us say I give a small input to this bob. Now, it has gone to some other location, right. There should be a restoring force which is trying to bring it back, right, only trying to bring it back, and that will be no given by the restoring force that it is creating automatically, right. So, that is what is stability about. So, this beta is actually as a result of a gust coming onto the aircraft from the side, right. So, what aircraft should do? Aircraft should kill this beta automatically, right, then only we will say that the aircraft is directionally stable, and that condition for directional stability is this derivative should be greater than 0, right, it is obvious. So, then whenever there is a beta created, you have to generate a moment, or the aircraft should automatically generate a yawing moment which is trying to kill this beta, right. Is this clear? Okay. So, we already looked at contribution to Cn beta because of different components on the aircraft, right. So, we talked about delta Cn beta because of the wing fuselage interaction, right, interference, and we also talked about the contribution coming from the vertical tail. Vertical tail is actually a stabilizer, right. So, it has to give you delta Cn beta which is positive, right. Wing alone can also add to Cn beta, but how will that come? How can wing contribute to this Cn beta? Because of the drag, right, so induced drag. Right, there will be a difference in drag on the two sides of the no two parts of the wing, right, two sides of the wing, and because of that there will be a yawing moment, right. And there is some contribution also coming from the engine plant, okay. So, it can be direct effect or indirect effect, but let us not bother about these two, they are very difficult to calculate, okay. Some expression is given for this term, okay, and this is very difficult to find out. So, if you want to have a better estimate of Cn beta, then you should actually include these two effects also, but then you have to find them from the wind tunnel testing or do a CFD calculation, but both of them are difficult. Okay, so these two are actually major contributors, and will not go beyond this. Okay, let's talk about so these two are major contributors. Okay, so this is about stability. What about control? You also need a control for changing the direction of the aeroplane, right? So, what is that control called? Rudder. Right? What is rudder? Rudder is a small flap attached to the vertical tail at the trailing edge, right. So, something like this. So, looking from the top, if this is a vertical tail, then this flap is rudder, right. So, what is rudder doing? What is rudder doing? So, same effect. Remember this vertical tail is a symmetric airfoil, and now you have this small flap which is rudder at the trailing edge of the vertical tail. When when you deflect this rudder, this small flap is going to change the camber of this part, right, and because of that there will be a change in angle of attack at the vertical tail, right. So let us so your velocity is coming, let us say, in this direction, right. You are going straight in a level flying condition, and this is the relative wind coming onto the tail, right. So I am now looking from the top. We can deflect rudder in two directions. One is this and the other one is this. So which one will give you a positive moment and which one negative? We are talking about yawing moment created by the rudder, right. And let us say CG is somewhere here. This one, because so you will get a force which is, for this deflection you will get a force in this direction, right. So the moment will be, so if I say this is the force y v, then I can take a moment of that force about the CG, and that moment is what? Positive, right, because x is going towards y. We always have to follow this rule, right. When x is going towards y, then it is a positive moment, right. That is what happening in this case, and that deflection of rudder is negative according to the convention, okay. So we are trying to always generate a negative moment by applying controls, right. In case of Cm delta E also it was negative, right. So Cn delta R is also negative, that is the convention that we are going to adopt. So this is your negative rudder deflection and this is positive, okay. So let us try to find out what is that moment. So we can add a sign, right. because this YV, the side force that is being created by this deflection is in the negative direction, right. Positive Y is this. This subscript is for V is for vertical tail, okay. Y is the side force. So, side force on the vertical tail is YV. Right. So, what is Cn? Cn is, now Cn is with respect to the wing reference condition, right. We are writing all the coefficients with respect to the wing reference condition, right. The vertical tail efficiency and tail volume ratio of the vertical tail. So, Cn is and this alpha is being created by the rudder, right. So, we can write this as so Cn delta R remember this is what we are going to need, okay. So, all the coefficients we do not really care about the dimensional numbers, right, because when we want to do the make the wind tunnel measurements, we are going to only put scale down model of the aircraft, right, in the wind tunnel, and then we are going to measure these coefficients, right. And this quantity, the change in angle of attack that you can get by the rudder deflection will depend upon the control surface area over the total vertical tail area, right. So, it is like a effectiveness parameter, and this is vertical tail effectiveness parameters, same as what you saw for the elevator. Or Now the question is, where would you actually need the rudder? In what all conditions you will need rudder? Okay. So we will try to list down all the cases where we will need rudder, right. And accordingly we have to size the rudder, right, depending on the requirement, right. So rudder sizing will be based on the requirements that you will have. Okay. So first thing is what he is saying is that there is an engine failure, right, asymmetric power condition. So let us say both of them are located at distance L from this center line, and they are producing thrust, right. There are two engines, right, one on each side of the wing, and they are located at equal distance from the center line, and let us say one engine fails, right. So if one engine fails, let us say the this one fails, what you are going to see? You are going to see a moment in this direction, right, and that will be T into this L. So you have to overcome that moment that is created because of this engine failure condition, right. So there you will need rudder, right, to fly along this path, isn't it. Second situation, yeah, turn. Okay. So what is happening, how you are turning? You are trying to bank, right. So how do you let us say so rolling is basically because of the differential lift condition, right. So even if one aileron is, let us say, at 0, and if I deflect the other aileron, it will give me a roll, right. So let us look from the front, okay, and see what is happening. So this is your wing, right, two sides, right. I am now seeing from the front, so I can see these two wings, right, and I want to bank my aircraft, right. So what happens, you have to generate lift on one side which is higher than the lift on the other side, right. That is how you will execute a banking maneuver, right. So let us say this is L plus delta L, while here you have only L. This will give me a roll, right, or bank, isn't it. What is happening because of that? So let's say this roll is positive, so x is moving towards y, wait a minute, y is moving towards z. So, you are getting a positive roll about x, right. Roll is a motion about the x axis of the aircraft. So, you are getting a positive roll, but what else is happening automatically? Because of this increased lift here, the induced drag will be higher, right, as compared to this. So, you are automatically also seeing d plus, right, d plus a change in small d because of this extra lift, right, and that is going to introduce a yaw motion, and which is against the roll, right. So, let us see if I can give you a better picture. So, I am trying to give the aircraft a positive roll because I want to bank, right. So, it is like this, right. Now, because I have increased lift over this wing, then only I can get this, right. I have increased lift over this wing, right, and let us say this wing has the same lift as the flying condition, right. So, you see a drag which is higher, right. So, earlier drag on the two parts of the wing was perfectly balanced with the thrust, right, and I was able to fly the aircraft in level, not accelerating, right, steady condition. But now because of this, there will be a moment because of this drag which will try to rotate the aircraft in this xy plane about the z axis, isn't it. So, it is actually rotating in the xy plane about the z axis to increase the side slip angle, right. Do I want that when I am banking? So, the yaw motion is exactly opposite to the roll motion, right. Roll you are trying to do in this positive sense, and you see a moment, yaw moment, which is in the negative direction opposing the roll, right. Everybody sees that? Okay. So, how do I now correct that yaw motion, right, while banking? We do not want to see that, right. When you are banking, you do not want your banking like this, you want to go this way and your aircraft will start rotating like this. You do not want to have that kind of motion, right, associated with roll or the bank maneuver. So, that is also controlled by the application of rudder, right. So, you can actually kill that side slip, and then the turn that you are, or the bank that you get, is called a coordinated turn, coordinated bank maneuver. So, this beta we have to kill using rudder. Any other situation which comes to your mind? This is definitely very important, both of them are really important situations, right. Of course, this may not happen all the time, right, but this is definitely a requirement because you will bank your aircraft in flight. Any other situation comes to your mind? Let us say you are trying to land, right, and there is a crosswind, and this wind is a constant wind. Okay. So, you should be able to differentiate between the two situations One is when there is a gust, gust is coming and going, and I am talking about stability with respect to that, right. Let us say I am trying to land, now there is a crosswind which is there, okay. It is not like coming and going, that crosswind is present. What will it try to do? It will try to take the aircraft away from the center line to which you have to align your aircraft to, right, when you are trying to land. Right. So, aircraft may try to go away from the line that is required to follow, okay. So, this is the center line of the airstrip, the aircraft is required to land on this line, right. So, the front wheels should touch along this line and you have to move along this line, right. So, in a crosswind, the aircraft may just go away from this line, right. So, that is where also you will need rudder, okay. You get the point? Is this clear? If there is a side wind present, then there will be a side slip, right, and the velocity vector of the aircraft is not going to, no, it is going to go in a different direction, right. So, the velocity vector is actually defining the flight path, right. So, it is having some beta which you need to kill using rudder. Any other situation? There is a angle of attack motion called spin of aircraft, okay, and that is because of the vortex, asymmetric vortex breakdown on the wing, two sides of the wing. So, you see a large yaw rate. Okay, so this spin motion is actually having large yaw rates. So, to control that you need so get out of this spin motion you need rudder power, okay. All right, is this clear? Yeah. Yeah. That is a good question, and unfortunately I do not have the right answer right now, okay. So, maybe for different aircraft it will be a different requirement. Okay, because spin motion, no, you will not usually fly a transport aircraft in at high angles of attack, but high angles of attack can automatically also happen when you have a situation called macro burst. It's a vertical column of air coming and spreading like this, right. So, if you have such a situation, then you know that while you are entering something like this, okay. So, vertical column of air coming down, and then let us say your aircraft is going like this, right. What will happen? Because of this increased velocity here, you will suddenly see a change in angle of attack, which can be large, right. So, these aircraft, actually the large transport aircraft and combat aircraft of course, they all have to be certified for this motion also, right. Only when you have the power to come out of spin using controls available, then you will get a certification for your aircraft. So, there is one more motion that we want to talk about, right. What is that? No, we have talked about stability in pitch and stability in yaw, right. So, what is left now? Stability in roll, right. And there are only two angles that we are talking about, right, with respect to which we are talking about stability. So, one is angle of attack and the other angle is side slip angle, right. So, which one will actually have to be encountered here, or which is the one which we have to care about in this case? No, which, alpha or beta, right? I am talking about two variables. Beta, right? Okay. What is going to happen because of angle of attack? Is it going to give a roll? Okay, not really. So, let's only let's talk about this angle beta, okay. So, we have a beta angle because of disturbance, right, and I want to kill that beta. So, which way the aircraft should roll automatically? Right, that is what we are trying to answer, right, roll stability. If there is a beta, which way the aircraft should roll automatically, so that the beta is killed. Right, we are trying to kill this disturbance, and here the disturbance is this side slip angle, right, small angle. How can you kill this beta? Through roll. Just now we talked about this. A positive roll is going to give you a increase in beta, right, isn't it? When you are trying to roll in the positive direction, let us say in a bank, beta is increasing. Can you use a similar argument to arrive at a condition where we are trying to kill this beta through the roll motion, and that roll motion should be automatic, right. I am not trying to use aileron or rudder to get this, right. The positive roll is going to give you a positive beta, you want to kill that beta, so you should have a negative roll, right. So dl over this L is rolling moment, okay, it is not left, okay. If you want to differentiate it, we can put a prime here, right. What sign this should have? Negative, right. Now L is Q S B into CL, this CL is roll moment coefficient. Okay, so these three remaining constant, this derivative also means, or right, and it is also called you have to remember that lateral directional motions are coupled, okay. So we can never talk about them separately. I cannot talk about yaw motion without talking about roll, okay, and I cannot talk about roll without talking about the yawing motion. So both of them are coupled motion, except the longitudinal motion, other two motions are coupled all the time. So this is called dihedral effect, and okay, so if you want to look at it graphically, this is what is for a stable airplane, right, because CL beta is negative here. Now less of CL beta, more of CN beta, or no, less of CN beta, more of CL beta, now it is a conflicting situation, right. Which one you want to design your aircraft for, right. So all that the coupled effect will be obvious when we are trying to talk about the aircraft dynamics, okay, actual aircraft motion using aircraft equations of motion. So right now we are only talking about static stability, we haven't yet started talking about dynamic stability, right. So let us try to look at some of the factors which can influence CL beta, right. Okay. Different location of wing in different fashion, okay, will influence the CL beta, and we will look at each one of them separately. So you can have wing sweep, right? Sweep back, sweep forward, dihedral, anhedral, high wing, low wing, right. All those situations we we will look at now. Let us say your wing is straight, right, and a wind is coming at some side slip angle beta, right. How would you calculate lift over the wing? What component of velocity will have to take? Normal component, right. So, let us say I am looking at this location and same location on this side. So, this is V and I want to find out the normal velocity that this particular section of the wing is seeing, right. That only I can use to find out the lift over that airfoil section. And I call this side 1 and this side 2. This angle is right. So, same length of this V vector I have taken on this side. Normal component is going to be same because there is a straight wing, right. So, lift on that airfoil section equidistance distant from the center line is going to be same, isn't it. So, it is not going to give me any roll, right. Okay. Let us see now you give a sweep, okay. Right. Okay, I think we will stop here. We will continue from this point in the next class.